Huge update for everyone.
Yeah, good. All right. I think we are recording now.
We're here. We've done it.
We have. All right. Well, mate, welcome back to another episode. Episode 18.
18 it is.
Getting close to number 20. We might have cooked up 16. Something happened with the audio, so we're going to go 15, 17, 18, and then we'll re-record the content from 16 in the future. But anyway.
It'll probably be better, honestly.
Yeah. Practice does make perfect, as they say. Mate, what part of the wild and wonderful world are you in at the moment?
I'm in Madeira at the moment, which is an island off Africa that is owned by the Portuguese. I don't think we use the word owned anymore. Is governed but is Portuguese. It turns out it wasn't inhabited. It was an uninhabited island as well, and then the Portuguese just kind of claimed it in the 1400s. But yeah, I'm here for a week to do a little bit of surfing, soak up the final rays of the Northern Hemisphere sunshine before I move back to Australia. So very exciting time. So we're going to do a few of these in person and definitely in better time zones.
Yes, that is for sure. Yeah, very good.
And where are you in the world, especially if the Queensland government asks?
Oh, yeah, still very much at home. I had COVID this week, so I've been at home all week, and it's made me go a little bit loopy, but I am free to roam the world again on the weekend, so that's good.
And you're feeling okay from the spicy cough?
Yeah, there's a couple of days it was kind of rough. Bad flu-like symptoms, that sort of stuff. Nothing too debilitating, but definitely pretty much back to normal now.
Yeah. And the big question, do you have a beverage? I don't have a beverage. I'm in a hotel room. I've got a sip of a peach iced tea left that I can pretend to drink, but
I've just got water. This is the first proof that I also own Yeti things. So I got my Yeti water bottle, but that's all today. Not very exciting.
They're a sponsor of the show. So.
Yeah, that's true. That's true.
Question: do you lose your taste?
No, I didn't. Oh, actually, a little bit, but I could taste things. But some stuff tasted different than what it normally does.
Okay.
Yeah. Anyway, let's get straight into it, man. What's on the cards from you this week? I don't know who's going first, but you can, and then I'll go next.
No, but you've got the hot, punchy topic, so I think you should go first. But I'll tell you what I'm going to talk about, and then you can tell us what you're going to talk about.
All right.
Because after 18 episodes, we still haven't figured out how to have a standard intro, but let's do it anyway. So I came across a paper in the last couple of weeks called "The Automated Discovery of Fundamental Variables Hidden in Experimental Data," and basically, this team from Columbia in New York took a bunch of data and observational data and got AI to predict the number of state variables within those physical systems that it observed. So they observed things like a pendulum, a double pendulum, and predicted the state variables. And a state variable is one of the variables of a set of variables that can be used to describe the fundamental properties of that system. So in the case of movement, the classic example is force equals mass times acceleration. Mass and acceleration are state variables. And yeah, they got AI to be able to predict the number and what these variables were within a set of 9 physical systems, which is really cool. So we're going to talk about that today.
Very cool. No, I like that. I'll find some videos that I was watching at one point that were sent to me, which were around a similar topic, which was like breaking down chaotic systems into these like weird low dimensional states based on some autoencoder setup. It was like, I have not watched them in enough detail to really give you a good explanation, but that whole space of sort of AI assisted science, I think, is fascinating. I mean, for me, the hot topic this week is stable diffusion. I got it running on my machine at home, messed around with it a bit. I think though that the one thing that I really want to talk about is everybody there's two parts of it. Everybody's very hyped about it, and it's cool, but it's also very fragile, and I don't think it deserves quite as much hype as it's getting. And then also there seems to be a trend that a lot of people have sort of said, okay, we've got Transformers now. That's the end. Like, we'll get AGI just out of bigger Transformers. And I think it's a weird mindset to be in, that there isn't going to be some next fundamental breakthrough in architectures, much like there was towards Transformers. So I figured that's what we would talk about today. I'm going to do another video solely on Stable Diffusion and some of the playing around I've done with it, but just generally want to talk about it today.
Yeah, good. Okay, well, do you want to jump into it? Give me a highlight. I've seen some of the outputs, and I think we should use them as the show's artwork for this week.
Yeah, for sure. Or what I'll do is you can do. So let me break this down. Stable Diffusion is it's in the same class of sort of text to image models. It uses a different technique. It uses diffusion, which is similar to not DALL-E 2, but it's similar to Imogen, the one that we talked about a few weeks back. The very cool thing here is that the team that produced the model, they've released the weights. It's a fairly small model in comparison. I think it's definitely under 2 billion parameters. It may be under 1. I can't remember the exact number, but it'll run on your GPU at home if you've got about 10 gig of VRAM. And that means that a lot of people have grabbed it.
How big was Google's again from memory? It was like 17 at some point.
Yeah. Massive. And I mean, obviously there's the training size and then there's the inference size and all that sort of stuff. But I think why this model has gotten so much attention is you don't have to join a waitlist to get access to it. You can run it on your own hardware. You can do what you want with it. You can mess around. And that's really led to a lot of people wanting to use it. And that's obviously in direct contrast to DALL-E 2, where you got to be on a waitlist, you got to have access, you got to pay for credits and all this other sort of stuff. But yeah, it's been around, and a lot of people have used it. A lot of people have done some cool stuff with it. But there's all these articles that I keep seeing, on Hacker News, Reddit, Twitter, everywhere else, of, this is the end of designers. This is the end of art and all of this sort of stuff. And my experience with it has been that it's fun and it's good, but it's not the end of art, really.
Yeah.
Like, it's very finicky to get things to be good. And I think if you wanted something consistent, if you wanted 3 photos of the same object in different settings, it would just take so much effort to get that you'd be better off just paying a traditional digital artist to use it.
What is different about this one to the other ones that is causing people to say this is it? Because we've talked about this already, so let's not rehash what we think about it. But why is this one different?
I think it's just accessibility, man. I really just think the fact that anybody can grab access to it and start using it is really great for a lot of people. There's a lot of websites where you can go around and, click through it and make some images for free. And I think a lot of the experience people had of DALL-E 2, for example, was they saw fairly well-known people on Twitter post results of stuff, because those were the people that were let into the waitlist, whereas here, anybody can do stuff. So, we shouldn't underestimate how big an impact that is, just the availability of it. But I don't know, it feels like it's captured the moment, definitely. But I don't know if it's going to be here for the long term. I think it's a fad, and it'll be fun, and then people will kind of see where it works and where it doesn't, and it'll, fade back into that sort of cool party trick sort of level at this stage.
And when you say fade, do you mean stable, or is in the space of AI generated imagery?
Oh, look, I think the current batch of AI generated imagery models, um, there's going to be a DALL-E 3, there's going to be a Stable Diffusion 2, there's going to be new architectures, new setups, new systems that make these better, and they get changed and they get tweaked and they find their niche. Don't get me wrong, there'll be a niche.
Yeah,
if you need some bottom of the barrel stock photography for your marketing copy and you don't really care what it is because it's going to be blurred and faded and blown up to some giant size, this will probably do the trick.
This will democratize some part of the graphic / artistic world and will give access to a lot more people to a certain part of it.
Yeah, exactly. Which is fine. But my feeling is that if that's what you needed in the first place, you were probably just like image search on Google, right click, save as anyway, and like not really giving a damn. So I don't know. I mean, I can see how if somebody worked out how to better, navigate these prompts and stuff, you could throw this into something like Canva and have a somewhat infinite library of potential images to use within your artworks. But the problem is they're kind of chaotic at the moment. Like I sent you a few when I was trying to make a podcast logo, for example, and some of them are like passably okay, but some of them are just like, I don't know, eldritch horrors is how people keep describing.
What did you use? It was so weird that it has to be good or something.
Yeah, like it's almost chaotic enough to be good. And it was like this half robot, half reindeer hybrid thing, like,
with headphones on.
It's funny and it's cool, and it's amazing that I can just keep clicking refresh all day and tweak prompts and do that. But yeah, I think it's cool, but it's not. I don't know. I don't think computers have figured out art yet.
And for the listeners, let's describe how low our baseline is for our logo. You described yourself as Elliot playing around in clip art. Elliot playing around in Paint for 2 minutes. You want a new logo. You have a very low bar for a logo.
Oh yeah, absolutely. So I'm not looking for something, that's going to win design awards. Although I did see today some AI generated artwork won an art contest somewhere. Which annoyed a lot of people. I don't think it was particularly like high caliber art competition.
Was it local Madeira kindergartens?
Yeah, colouring in.
So let's talk about the mechanics a little bit of Stable compared to some of the other image generation models.
Mm-hmm.
Is there anything wildly different to it, or compared to the others, or is it working a similar way?
It's similar to Imagen in that it's a diffusion-based model. I think the variations are around, where it gets the same as Stable Diffusion, which is sort of a modification on this diffusion, and I think it's the sampling part of the process that's slightly different, which generates more consistent results.
Can you explain that bit a bit more to me? What the Stable Diffusion aspect is?
So the way these diffusion-based models work is they model the image generation process as there was once an image, and then we kept applying noise and shifting pixels around and just muddling them all up. Like if you imagine each pixel was a colored piece of sand, and then you just sort of shake the tray that it's in.
Yeah.
Over time, that's going to look more and more like noise. And the AI learns its process of, okay, how do we unshake the sand? If I get a shaken thing of sand, how do I move the pixels back to a point where it kind of looks like an image? And there's lots of different ways to model that process. Obviously, from pure noise that was never really an image, you are just learning a way of approximating images from that noise. And the different models have different ways of judging how to shift pixels around, and I guess the heuristics, apologies, that they use for that process.
Okay. And was there anything magical or particularly inventive about Stableware that meant that you were able to run it locally?
They just designed it to be smaller. So it's using a smaller text embedding setup. It's using a smaller sort of image-to-image type bit, which is a UNet. It's like, I mean, it's large, but it's not as amazingly large as, you know, DALL-E 2 or anything else.
And have they done it in a smart way that the performance sacrifice is minimal?
Yeah, I would say so. Like, it generates pretty good results. But we've seen things like Hugging Face had an app up called Mini DALL-E 2, which people could go in and plug in, and that was much smaller. Like, the image quality did sacrifice there a little bit, but you can get away with smaller models if you want to. I've not seen a head-to-head on the same prompts and things between the two. And I don't know whether that would be meaningful, but the results are pretty good.
Yeah. If I remember back, what was Google's model's name again?
Imagen.
Yeah. If I think back to Imagen, right, it had a step change above like 7.5 billion parameters or something like that, right? It was like everything below that was kind of looked about the same, and then there was a step change at quite a large level where the performance drastically improved.
Yeah, definitely. And some of the stuff that DALL-E 2 and some of those smaller Imagen models struggle with, like text, Stable Diffusion definitely struggles with as well.
Yeah.
But in terms of, I just want to make some images on my computer, it definitely crosses that bar.
And would you categorize this as and I don't want to belittle the work, but an iteration or an innovation?
I think there's innovation in here, but the work that this research group did, and much like any of these other models, is that they add a small piece and make a small contribution to the literature at large and combine that into something useful. Much like DALL-E 2 and Imagen are well-known text encoders on top of well-known sequence-to-sequence models or anything like that. This model as well is a combination of known parts with some small innovations on top, which make it practically functional in the real world.
Yeah. Well, maybe we could switch gears for a second on this. And this is something I heard recently in a couple of weeks, which is kind of related to this topic, which is about an application for this type of AI and the models in the image generation space. And that is that kind of overlaps with the metaverse. Well, definitely overlaps with the metaverse. And a big question that people that are deep in the metaverse and proponents of the metaverse have is who's going to create all this content for it, because we're going to need so much content and we're going to be able to create so much personalized content. And if you look at the corollary between, let's just say, Instagram and the metaverse, what unlocked Instagram was people able to easily produce their own content through phone cameras.
Mm-hmm.
And it meant things like Instagram, social media were able to, like, obviously social media taken off at that point, but like the ability to produce your own content coincided with these trends and made them much more sustained and embedded, because people were able to create and share and engage in certain ways. And a big question for the metaverse is how can we switch from a content consuming world to a content producing and consuming world? So how can users create their own stuff? And it gets a little bit more difficult in the metaverse because you're moving from point a camera at something, click a button, to creating 3D models of things. And that's a pretty niche skill to be able to create 3D content for the for the for the augmented and virtual reality worlds. And one hope that and I heard this week, is one hope that a lot of these people has is that AI will help with this space of being able to help people produce their own content for the metaverse. And I thought that this was this is the first time application other than like graphics designers aren't going to have a job that I've heard where I've sat up and gone, okay, that's something I can believe. Let's hear a bit more about that. So yeah, that's something I heard this week, and it kind of jumps into this. So like, do you have any reactions or thoughts to that about how AI will help the metaverse really?
Yeah, it's an interesting one. I remember, gosh, how long would it have been? Probably even close to like 15 years ago, when you remember Second Life?
Mm-hmm.
That game, and a lot of the like premise of that game was user generated content, and like people could build their own stuff and write their own scripts and all this sort of stuff, but it was kind of inaccessible to a lot of people. So I can definitely imagine that if you can, create some things, like let's say you want a race car, you describe a race car and it creates a base model for you, and then maybe you tweak it with some tools within product. I do see that as a way to really fast track a lot of this creation process. I think your point about Instagram is really an interesting one, in that anybody can write a prompt. It's not a very hard thing to learn. And so I really do think, this does open the door to, if you can make that prompt turn into something highly valuable, that could be a really good way to start bringing a lot more individual creators into the content creation process, which again, I think is why Stable Diffusion has done so well. How this translates to 3D and more sort of interactive live experiences, I think there's still a lot of work to be done. Just the models to output those, like, I haven't seen any good ones yet. Certainly not to the same level of, I guess, human quality radar that these image generation models have, but they'll come for sure. I would not doubt that they will arrive.
Are there any models that work on the tweaking aspects? So for example, it's like when you're making the logos, you got it to a point, pick one, and then ask it to change, get rid of the deer-like features on the robot and make it look more robot. Are there tweaking features to these things, or is it start again? I've never used them, so I don't know how the mechanics of like this works.
Yeah. So with this one, there is an image-to-image mode where you can supply an image and a prompt, and it'll use that image as a base and make some modifications. So you can do that to, tweak styles or try and remove things and other bits and pieces, and it works okay. If you're willing to iterate a lot, you can usually get something okay out of that. The other way people have used it is they'll draw sort of a Microsoft Paint level picture of something, let's say some mountains and some trees and some people, and they're all stick figures and stuff, and you'll use that as a base, and you'll say, an oil painting in the style of whoever, based off this image, and it'll do that transformation. And that, I think, is actually genuinely very, very cool.
Okay, very cool.
Yeah.
Very cool. Well, any other thoughts or closing comments on this?
I think just the other point, two things. The thing that I will do for this artwork for this episode is I will take our normal artwork and I will run it through the image-to-image mode, and I will have us in the style of an oil painting or whatever I find that's most funny. But the other thing that I think is worth pointing out here is that, Transformers have definitely taken the AI world by storm. Like, everything is Transformers now. But I think amongst those that are sort of on the peripheries of AI, but maybe not as deep into it, there seems to be an opinion that that's it. transformers are the end state. We've solved it. Everything is done. And I would caution people against that, in that there will be something that knocks transformers off their throne. There's still a lot of people doing fundamental AI research in architecture design and things like that. So, don't count the race as won just yet. We've reached our current plateau in the world of stacking S-curves on one another, but there will be another S-curve out there that is going to come forth and really change this in hopefully the same order of magnitude as the sort of LSTM to transformer way did.
And if you'd like to learn more about transformers, watch our video.
Oh yeah, I forgot we did a video on that.
When people generally say like, oh, well, we reached a plateau, it's just generally like, to me that says that there's a couple of core assumptions that people are assuming are invariable. This might be a bit of a tough question to put you on the spot with, but what do you think people are assuming that makes them think that transformers are it?
So I think the biggest one is
what theoretical limit, like the speed of light, have they hit?
I don't think it's that. I think people have felt that what we need right now is just more scale, more data, bigger models, and that's going to be where we get the breakthroughs in performance. And there is some evidence to say that that's true. We looked at that paper the other day around the size of different models and the parameter counts and how that affected performance. But I don't know. It's to me, it's almost like if you were selectively breeding horses and you were comparing what feedstock they had and all this sort of stuff, and you're like, look, we learned that if you breed with this rare, ginormous horse, you're going to win 99% of races. Therefore, we know the answer to all this. And then someone comes and invents a motorbike, and it's just no competition anymore. Yeah.
It's also definitely one of those things where, like, if it's software v hardware people are always going to say that software is to blame, and software people are always going to say hardware people to blame.
Yeah, for sure.
Yeah. Okay. Well, very cool. I'm excited to see what I look like in Rembrandt style, for our episode art this week.
It'll be good. It will be good. It'll be funny at the very least.
Awesome.
Yeah, good. Well, man, your topic.
Yeah,
tell me more.
So it's a couple of weeks old now, but I thought it grabbed my attention, so I thought I'd dig into it, and there was a paper behind it, and it seemed to be pretty well received. It seemed to be pretty well written, and it came from a pretty well-respected place within Columbia University. And I thought it had a couple of the investigation itself could lead for us to have a couple of good questions around, like, the applications of AI in just helping us discover things rather than just produce or solve certain things. So, I wanted to jump into it. So, as I said earlier in the show, the paper was called "The Automated Discovery of Fundamental Variables Hidden in Experimental Data." And the short of it is that this research group from Columbia gave their AI model observational data through video on 9 physical systems, and they asked them to predict, one, what would the future state look like, so create an image of what you believe it would look like in the future. From that, determine what are and then from that determine the number and what are the state variables of the system that guide this. As I said, state variables are the core variables that describe a system. So for mass times acceleration equals force. Mass and acceleration are state variables. There's a couple of cool things that we can talk about today. The way they did it, why it's important, but and then also as well, like, just some general meta questions around it. But what I'll jump into first is, like, why the researchers went out and did this and why they thought it was important. And they went out and to explore this because their view is that, look, we have state variables for a lot of things out there, for example. So, simple physics, thermodynamics, stuff that you learn in high school, we've got nice governing equations for and nice variables that we can measure. But in a lot of the modern physics, especially, for example, in the particle physics world, observation and data is well outstripping theory. Yeah. So, for example, the Hadron Collider, the last time they ran that, I remember reading something like they were going to spend the next year and a half to 2 years compiling the data.
Crazy.
Yeah. And they run this thing only every couple of years because basically we can't keep up with it. And, well, there's also the risk of just accidentally creating a black hole. And so the authors wanted to explore this of in areas that we have so much data and observations that outstripping theory, what could we be overlooking as humans, and what could benefit from using AI to help us understand of what are the core variables in a system? And this isn't about press the button and AI is going to go discover the new E equals MC squared for us. But to them it was about, in these fields, how could we use AI to help us hone in on the right things? So I thought that was a really, really cool question to ask. And I'll just quote this from the author themselves, which says, "What if we could explicitly identify the intrinsic dimensionality of a system and the corresponding hidden state variables purely from the visual information encoded in raw camera observations?" So that was the. So what if we gave the AI data and we could get the hidden state variables out of it? What if we could discover mass and acceleration equivalents in other fields from AI? Which is a really, really cool question to start with. So I'll jump in and tell them now about how the AI works. So the best way that I can figure it out is what they did is they gave a neural net a bunch of physical dynamic systems. So they gave them a lava lamp, they gave it a flame, they gave it a single pendulum, they gave it a double pendulum, they gave it swirling diffusions, they gave it a swing stick, which is one of those things you keep on your desk that swings around. And what they did is they asked it to make they gave it all of the past states, and then asked it to predict up to 1 second in advance what it think it would look like in the future. And what it was able to do was accurately able to do that. Then what they asked it to do is they asked it to go, right, now that you've accurately predicted the future, what is the minimum number of variables? And by the way, you get to determine what your variables are. What is the minimum number of variables, independent variables, that you would need to be able to make this prediction? And they did this with I'm just going to say some words here, and if you can explain to the lovely people what they are, because I was struggling to understand them, that would be great. But they did it via a neural network with bottleneck latent embedding, which is a bit beyond my pay grade. No, okay. So after they did that...
Oh, you want me to do it as we go? Sorry.
Yeah, go for it.
Yeah, so, I mean, my guess would... So the neural net, hopefully, is not above your pay grade.
No.
What was it? Bottleneck?
Latent embedding.
Yeah, so what that often means is that the representation, either on the way through or at the actual embedding level, undergoes sort of massive dimensionality reduction. So, for example, a video, or let's just say an image of a lava lamp might be 512 by 512 pixels in 3 channels. By the time you've gotten down to a couple of layers deep, your image is certainly smaller, but you've got all these different feature layers. So you've got a lot of different variables explaining that scene. What bottlenecking does is it says, neural net, you're only allowed to keep a dozen features to describe this entire thing. And So it just drastically reduces the amount of available features, which can help with things like compression and also, in this case, I imagine, simplified representation of the system.
Yeah, it is first. So what they did is got some bad data, asked it to make future predictions about what it was. When they got that right, they then bottlenecked it to like determine what is the minimum number of variables that you could be doing this with, and then to determine actually what variables they were and what those variables represented. They then came back to that model and said, right, I want you to reconstruct the future images over the next 1 second again, this time only using the minimum number of variables that you said you needed, and to reconstruct the images. And from that, they were able to like determine the kind of like the exact variables that the AI was using. Now, they don't actually tell you what those variables were because they're actually dimensionless and they're all visually based. But
yeah, right.
And I'll jump into now the results of this, is they were able to correctly predict the future of these systems with the same number of variables that humans have minimized this, with the same number of state variables that humans use. So, for example, for a single pendulum, you only need two variables.
Mm-hmm.
I think it's the angular velocity and I think the length. And yeah, it was able to determine that it only needed two variables to predict the future state of a single pendulum. It got it right for the double pendulum, it got it right for the swing stick, it got it right for the diffusion. But interesting things like the lava lamp and the fire, which are considered chaotic, it came up with a number. We don't know what the actual number is for the state variables for describing a flame, but it came up with one of like 40 state variables to describe a flame, which is really cool.
No, that is interesting.
And so they kind of measured on a couple of things. First is like, could these things the first step out of all of this was like, could their neural nets accurately predict the future state of these 9 dynamic systems? The answer was yes, they could, and it passed on a bunch of different image tests. The second one was, could they accurately predict the number of variables for the physical system? And as I said, they did it all correctly for the systems, for the known systems. I think it ended up with like there was, it was like very close in most of them, because they did like a mean and a spread from the different types of models that they used. But like, for example, the double pendulum was 2.05, but the actual answer is 2 or something like that. So, and then interestingly as well, they then did the long-term stability prediction. So over this 1 second, because these systems, a 1 second within a chaotic system is a long time. Like, what is the success of predicting these things? And they were able to show that they're called the neural state variables, were able to predict quite well from a long-term stability point of view for all of these systems once again. And one super interesting part of the paper that they didn't really highlight, but I just thought it was really cool, is that when they were doing this long-term prediction, they compared two things. They compared it when they had like 60,000 dimensions within their predictive algorithm, or they had it when they had this number of state variables, so like 2 or 4. And the one that had the most amount of variables in it just performed terribly at long-term prediction, and the ones that had the state variables performed really well. So a reduced number of variables performed significantly better in long-term stability than the one with thousands of variables, which was like kind of an interesting outcome to me, because it showed that when you introduce thousands of variables into a system that doesn't need it, you're probably going to introduce noise very, very quickly.
Yeah, definitely. And I think it's a good indication that whatever this model is learning is actually something functionally useful at that low dimension state. Yeah, cool.
So that's a bit of a rambling overview of this paper, but the core of it is that they gave AI that had no prior knowledge of human physics of these systems, and it was able to come to the same conclusions as humans about our known about the known systems and come up with some hypothesized new state variables for some new systems like a flame and a lava lamp. And that then poses the question of, or then leads to the next point of like, okay, cool. Last time we ran the Large Hadron Collider, we came out with the Higgs boson, and as I said, like 2 years worth of data crunching. If we're trying to explain something in particle physics, and as I'm quickly stepping outside my pay grade, and I don't know the questions to ask here, but if we're trying to ask something within particle physics, the equivalent of the flame, and understand how many state variables it have, imagine if the scientists had this tool alongside it and were able to suddenly realize that, you know what, we have this amount of data that's going to take us 2 years to work through it. What if there was only 50 things in this that we actually cared about?
Yeah, absolutely. I mean, imagine, how many problems we have that we could throw this at, both in the sort of traditional physics sense, but also, like economics, sort of behaviors of crowds and all that sort of stuff, where there may be some pretty low-level fundamental truths just waiting to be discovered.
Yeah, so there's hundreds of interesting problems that we could probably list off in the next 20 minutes that we could think of. One that I have as well is like, what would this do for the unsolvable math part, the unsolvable parts of the world? So, for example, like chaos theory, and the idea that, predicting the weather, that as soon as there's like even the slightest perturbation, all of the or like rounding assumption, everything goes incorrectly. I wonder whether there's certain systems out there that we've assumed are chaos, but we haven't been able to figure out the underlying state variables in.
Yeah, it's certainly possible. Whether that's, there's more than we gave consideration to, maybe the weather needs 15,000 variables to get stable predictors. Yeah. Or even the alternative, which is maybe there's things we should have been looking at that we just never were.
Yeah. So one question that I was thinking about when I was bringing up this topic is like, are there, like, we talk about fundamental discovery as an area where AI could help us discover. Like, obviously, AlphaFold has been one of the most probably like newsworthy discoveries recently. But is there anywhere else that you've come across that we're using AI to help us discover rather than to solve?
Oh, I mean, a lot of the ones that spring to mind are very theoretical and along the same lines as what we're talking about here. But I think, there's the AlphaFold class of problems, which tends to be kind of like a search problem in that, like, there's a massive state space of possibilities and we just need to find viable candidates. But we can describe that state space pretty well because it's a physical configuration of some known parameters. We just don't know which combination is correct. And then there's things like you're talking about here, like data out of super colliders, which is like, look, it's raw data. We don't know all of the underlying physics, and that's what we need to discover, which I haven't seen a lot of, but I think is a very exciting and probably underutilized at the moment application of artificial intelligence in science. I think, though, that you made a point earlier that is worth coming back to, is that we don't know what the underlying variables that this AI model picked out were, and we can get a good feeling that if there's 2 there and 2 here, there's not many choices of 2 variables that are going to be different from the ones we knew. But in more complex scientific situations, we need to think, okay, how do we get something interpretable out of these models in a way that it says, okay, here are these 2 variables. I've named them, Schmorse and Schmass. Yeah. And if you do, whatever the equivalent to Newton's laws are, it all works out. And we say, okay, cool. That's translatable. That's testable. Sure, use different words to us, but I kind of see that translation. Whereas if it's, look, there's 8 secret variables that control the universe, and nobody's going to tell you what they are, but trust me, there's 8 secret variables. I think it may lead to a sort of dissuasion in science of, I guess moving towards science in that field being more of a data churning exercise as opposed to sort of a fundamental understanding of the underlying system.
Yeah. Yeah, and when you said that, you made me think of as well as like an issue that this space could run into very quickly as well, is like restricting observation to a single medium of observation. So this has been a visual via video observation, right? Like you could make a model that is incredibly good at doing this, right? Where it takes video from it determines state variables from image observation or video observation. But like if you try and do that in the Large Hadron Collider, right, like you're just going to be making spurious correlations because you're missing a significant amount of the observation that's required. Like a good example in this situation would just be you're missing mass, right? Mass as in the mass of the object. Like you can only do so much prediction of Newtonian physics without mass, and you can't really determine mass from a video.
Yeah, I think it would take quite a long time for the AI to work out that mass exists, especially, if all of its videos were, bodies acting under Earth's gravity and things like that. There's probably a lot to be said there about how you encode your data. And I think with AlphaFold and this work and any other work, a lot of the effort is how do we take the real world and encode it into something that we have good AI models for, whether it's sequence to sequence or search or anything else, which is still a huge task. I think a lot of the success of AlphaFold has come out of the ability to codify, protein sequences and also the sort of 3D structural information about proteins in a way that is amenable to AI. But if you didn't have that, if you just gave it, protein codes and then, I don't know, generate a full 3D model or something like that, is just like you need to generate every particle of or every sort of voxel of space, I just don't think it'll work nearly as well. So this encoding, decoding step is definitely a big part of this.
Yeah. But the flip side of that is if you're sitting in space with an incredible amount of data that you already know and you're sitting there scratching your head about how it all fits together, you should give these people from Columbia a call.
Well, definitely. And I mean, I would definitely not discount their work just to that situation in that, if we can combine those two ideas, who knows what this model is going to discover. Let's not bother making it rediscover Newton's laws of physics other than to prove the point. Let's teach it everything we know and then say, all right, you know all that, now go out and find what we don't know. And I think that's where it starts to get really exciting.
I wanted to talk about this high dimensionality being not important in the long-term prediction. I just found that fascinating because I think we often come across throw more data, throw more variables at it as a solution to a lot of problems. But in this situation, it just didn't improve it. In fact, it made it worse. And actually minimizing the number of variables to describe the system, which we know is the correct answer, drastically improved the predictive capabilities of the model. And we've talked about this in a number of different spaces as well. I think we talked about it in episode 16, which you'll have to listen to afterwards, called the Piranha problem, which is generally if you have too many variables, then you're probably mismeasuring some of those variables, or those variables are actually just describing other variables within. Basically, the sum of it is there's only generally a couple of variables that will impactfully describe your system, and this seems to be the case here as well.
Yeah. And, I don't doubt it. And I mean, in sort of traditional optimization settings, you can characterize a problem as sort of undersolved, critically solved, or sort of
Yeah.
oversolved. And the example for oversolved is that for any number of points, let's say you have 1,000 points, you can create a polynomial of degree 1,000 that perfectly fits every single point. But if you were taking those 1,000 points as, noisy samples from a real world event, and you said, I'm going to make a degree 1,000 polynomial, within the data that you have, it'll fit fine. But as soon as you go outside the bounds of your data, it's going to just blast off into some random dimension because you pushed and squeezed it so hard to fit. And I think that's what's happening here. And it's amazing that the AI is sort of mimicking that behavior and starting to learn these simple representations as well.
Do you remember in Little Excel when you had your ask word value of your data, and you could just like do a line of best fit, and you could do a polynomial fit, and you could just keep pressing the
Yeah, exactly.
I think they tapped you out at 99, but I'm pretty sure I probably lied on some science project once where I threw up the x squared, like the polynomial to 99, took the r squared, and then dropped the best fit back down to the cubic or whatever they wanted us to do for the project.
There you go. You would not make a good AI in this case.
Well, good cheating AI.
Yeah, true. Oh, very good.
So yeah, it's I do recommend having a look at the paper and also the prediction of it. It's incredibly accurate, how they predicted the lava lamp, which I did fluid dynamics a little bit back at university, and predicting a friggin' lava lamp, that sounds like a meaty project that would have taken a long time to do back in the day.
Yeah, I mean, those are supposed to be so chaotic that there are data centers that have walls of lava lamps and video recordings of lava lamps to use as their source of entropy for their random number generation.
That's cool.
Yeah. So, I mean, thankfully it didn't crack that one, because there's probably be some security implications somewhere had it done that. Very good. Well, maybe we're coming up to time, and your battery is, being run down as we speak. Any other last little things you want to plug before we sign off?
Nothing new. Just our deep workbook review is getting a lot of hits. So if you haven't seen that, check it out. People are liking it. So that's been going well on the channel the last couple of weeks.
Very good. Yeah. Please check out our other videos. Hello to our 30 subscribers, the big 3-0. That's a nice number to be at. We'll have some more videos coming back more regularly now. Tom and I have both been having a little bit of downtime, but back at it again.
20 we'll try and do it in person.
Yes. Yeah, that'd be good.
We might have to do it in a 19A in between, but
yeah.
we'll just record 21.
Yeah, exactly. All right.
Good stuff.
Well, I've lost your video again, so that seems like a great time to call it. Thank you very much, everybody, for listening, and we'll talk to you again very soon. Friends.